And the last session you have seen the frequency analysis. In this frequency analysis, we are going to discuss about the Bode plots and the polar plots, Nicholas charts and Nyquist plots. And the today's session we have to discuss about the what is the Bode plot and what is the procedure to construct the Bode plot. So, in this session, after completion of this session, you can understand the Bode plot and how you are going to construct this Bode plot. These topics we are going to cover. So, the Bode plot or this Bode diagram, generally it is having the two types of the diagrams we are using. One is the magnitude plot and the second one is the phase plot. In the last session already we have seen how you are going to determine this magnitude of the given transfer function and the phase angle. So, now we are using those the formulas to determine the magnitude and phase angles of the different transfer functions, and in this today's session I want to explain what are the different transfer functions and each transfer function, how do you determine the magnitudes and phase angle, and what are the step of the procedure to construct the Bode plots we will see. So, in this both the plots that the x axis represents the angular frequency and y axis representing this magnitude as well as the phase angle. So, at one part you have to representing the magnitude and frequency, and other part you have to representing the phase angle and frequency. So, the y axis representing the magnitude, all are in this the linear scale, and the transfer function of the magnitude plot and the phase angle we are representing the y axis, and we will going to construct. And how do you find out the magnitude of the given transfer function? So, because it is using the logarithmic scale, you need to construct this the plots, and the magnitude of the open loop transfer function, that units is in the decibels, and that is calculating using this m is equal to 20 logarithm of modulus of the given transfer function, that is g of j omega into h of j omega. And the phase angle of the open loop transfer function is in terms of the degrees, that will be calculating, that is the angle of the given transfer function j of j omega and h of j omega. So, the base of this logarithm is for all these take 10, and we have to while calculating the magnitudes. And the basics of this Bode plots, what are the basic terminology we are using to construct the Bode plots are shown in this next slide in the tabular form. Now, see this what are the different terminology, okay, and each terminology how do you find out this magnitude and what is the phase angle. So, now you can see this at the constant, if you have this any constant function, the transfer function is only the constant value, then the gain value this g of j omega and h of j omega is that constant k, okay. And the slope for that the curve is 0, and here the slope is we are calculating, and we are drawing this curve with the slope of the per decade we have to calculating. So, the decibels per decade, that 0, and the magnitude you can calculate this 20 into log of k, whatever the k value is there, based on that k value you are going to find out the magnitude and the phase angle. Here in this case, if it is a constant k, the phase angle is 0. So, these are the values are very much important while constructing the Bode plots. And 0 at horizon. Generally in this transfer function we have the zeros and poles, and what are the zeros, whether any zero is at horizon is there, or whether any pole is at horizon is there. Based on that you have to first find out what is the magnitude value and what is the phase angle. So, then you will go for the plot these Bode plots. So, 0 at horizon, so that is the s value. So, s is representing the j omega. So, j omega, if the function, the transfer function g of j omega, h of j omega is equal to s, that j omega, then what is the slope? The slope is 20 decibels per decade, 20 decibels, each decade it changes the value of 20. So, 20 decibels per decade is the slope, and magnitude is 20 log omega. At different frequencies we are going to find out what is the magnitude value, and the phase angle is 90 degrees. The phase angle is 90 degrees, that is 0 at horizon. Now, similarly, nth power of zeros at horizon, nth power of zeros at origin, simply these values you can multiply with this n times. Okay. So, then you have to obtain, that is j omega to the power of n in the given transfer function. If it is in this form of s to the power of n, then what is the slope and what is the magnitude and what is the phase angle we are going. So, that is simply you have to, whatever the 0 at horizon values are there, simply you have to multiply with this n times, then you can obtaining the slope and the magnitude, phase angle, that is 20n, 20 log omega and 90n is the corresponding value, slope, magnitude and phase angle. Similarly, the pole at horizon, if pole at horizon, that is representing the 1 by s, that is 1 by j omega. So, what is the slope? If pole at horizon, the slope is minus 20, the slope is minus 20 and magnitude, that magnitude is obtained minus 20 log omega, the magnitude is minus 20 log omega. At different omega values, you are going to calculate this magnitude values, and the phase angle is the minus 90 or 270 degrees. So, that is the pole at horizon, the pole at horizon representing the 1 by s, and that is equal to this 1 by j omega, this is 1 by s. So, s you can replacing the j omega. So, the pole, similarly how we are find out n zeros at origin, similarly here n poles at horizon. So, that is 1 by j omega to the power of n, that is 1 by s to the power of n. So, 1 by s to the power of n, if any given transfer function is given, then you can find out what is the slope and magnitude and phase angle. The slope is minus 20 n and magnitude is minus 20 log of omega, and the phase angle is n times of this value minus 90 n or 270 n. For constructing the Bode plots, these are the terminologies you should aware, and once you are awareing all these terminology, then it is easy to, for this simple the transfer function goes to the complex transfer functions, and that complex transfer function dividing to the simple basic factors, and each factor you have to separately draw the diagrams, and combining these two, then you are obtaining the final Bode plot, final the magnitude plot and phase angle plot. So, for that we required all this information. Now, see this the simple 0. In the earlier we have seen the 0 at origin. Now, it is not at origin, it is a simple 0, that is representing the transfer function is 1 plus j omega r. The transfer function is representing 1 plus j omega r. If it is 1 plus j omega r is the transfer function, the slope is 20 decibels per decade. Slope is 20 decibels per decade, and magnitude is varying according to this value of the constant r, according to the value of constant r. If this value is that omega, the omega is less than 1 by r, omega is less than 1 by r, then the magnitude is 0. Magnitude is up to this r value, up to this r value, the magnitude is 0, and behind that this magnitude is changing with a slope of 20 decibels per decade, that is 20 log omega r. So, for omega is greater than 1 by r, if omega is greater than 1 by r, and this curve is a straight line with a slope of 20 decibels per decade. And what are the phase angle? The phase angle is also similarly for the 0, for if this omega is less than 1 by r, or if it is 90 for omega is greater than 1 by r. So, according to this value, that the constant of this s term, this generally we are representing, this is a 1 plus s r. Okay. And according to this r value, you have to see that whether it is the slope is 0 or it is having the some slope, that you have to calculate. So, up to this value 1 by r, if omega is less than 1 by r, the slope is 0. It is a straight line with a given the magnitude. Okay. And from that it changes the slope of with 20 decibels per decade. Okay. Now, we will see that while constructing this Bode plot, you can easy to understand. Before that I just want to explain what are the different basic factors we are using to construct the Bode plot. So, similarly you can use the simple pole. The simple pole is representing like this 1 by 1 plus s, the 1 by 1 plus s, okay, and some constant here, if it is having any constant, that r. So, 1 by 1 plus j omega r, then here the slope is minus 20, the slope is minus 20 decibels per decade, and the magnitude here also you see that 0 value up to the omega is less than 1 by r, and the behind that this slope is minus 20 the log omega r if this omega value is greater than 1 by r. So, up to this the 1 by r value the slope is 0, the constant straight line, then behind this it changes with a slope of minus 20 log omega r, that is so minus 20 decibels per decade. Similarly, the phase angle is 0 if omega is less than 1 by r, and it is having the minus 90 to 270 if omega is greater than 1 by r. Okay. Now, these are simple have seen up to now, thus 0 at horizon, pole at horizon, and simple 0 and the simple pole. Now, we will see that the second order derivatives, okay, and second order the integral form, then these are the slope is 40 if it is a second order derivative term, the slope is 40, and the magnitude is obtained the 40 log omega n, and the for omega is less than omega n, and if it is 20 log of 2 delta omega n square for omega is equal to omega n, and 40 log omega for omega is greater than omega n. So, that omega value from this the omega, whether it is less than omega n or equal to omega n or greater than omega n, at 3 different stages we are obtaining the 3 different the magnitude values. Now, we have to find out this phase angle also 0 for omega if less than omega n, and if it 90 degrees if omega is equal to omega n, and it is 180 if omega is greater than omega n. So, this is for the second order derivative term. If in a given transfer function, if it is having the second order derivative term, then we have to use this concept to find out the magnitude and phase angle. And if given transfer function is integral form, then if it is integral form, then we have to find out the slope is obtained minus 40 decibels per decade, and the magnitude you are going to calculate according to this omega value. If omega is less than omega n and this magnitude is minus 40 log omega n, and if it is omega is equal to omega n, then this magnitude is obtained minus 20 log 2 delta omega n square, and if it is greater than omega n, then this value is minus 40 log omega. And similarly find out the phase angle, that is minus 0 for omega is less than omega n, and minus 90 for omega is equal to omega n, and minus 180 for omega is greater than omega n. So, according what are the basic terms we are using, based on this basic terms we are going to calculate what is the slope and what is the magnitude and what is the phase angle. Okay. So, for any given transfer function, before constructing the Bode plot, we need to calculate for each, at each we have to take the several values of this frequencies. Frequency we have take from this, let us from 0.1, frequency is omega is equal to 0.1, what is the slope, magnitude and frequency, and omega is equal to 0. So, what is the values, and omega is equal to 10. So, at each 10, because we are taking for each decade the slope also we are taking the some value for decade. So, each decade, so we have to calculate frequencies corresponding to the magnitude and phase angle. Once if you know this magnitude and phase angle corresponding to the frequency, then you can easy to draw the Bode plot, the magnitude plot and phase plot. And for constructing these plots, we require the logarithmic plots. And using the logarithmic plots, we are going to construct the magnitude plot and phase angle plot. And after constructing this Bode plot, that magnitude and phase angle, and where the crossover frequency is occur, you have to notify, and corresponding to the crossover frequency, what is the margin you have to identify, and that margin is you have to see that whether gain margin or phase margin, and based on that value gain margin, phase margin, whether the given the system, control system is stable or unstable, and at which frequency it will bring to the stability, at what job that stability, that frequency also we are going to easy to find out using this Bode plot. That is the main advantage of constructing these Bode plots. So, this basic factors we will see that how your simple construction of the Bode plots. Now, we can take in this basic factor, the transfer function is simple, the constant k. Just now in the tabular form we have seen calculated what is the slope, magnitude and phase angle. Now, we will see that how the graph will be obtained at different k values. Okay. The magnitude you are going to find out m is equal to 20 logarithm of k and in terms of decibels, and phase angle is equal to the pi is equal to the minus tan inverse of the real imaginary part by real part. Okay. If there is no real part, imaginary part, this phase angle is 0. If at different k values, what is the value? If k is equal to 1, then this magnitude, substitute k is equal to 1, the magnitude is 0, and if k is greater than, then this value is obtained some positive value. If k is less than 1, and this magnitude is obtained the negative value, and the corresponding Bode plots shown this as for these values. We will see this how they looks like the Bode plot. The simple the gain constant value is given. Okay. Now, we are constructing the taking the frequency on the x axis and magnitude on the y axis. So, now we had see that a k is equal to 1 and it is a 0, and k is greater than 1, it is a positive value. At some positive value we have to draw this straight line, the slope is 0. So, it is a straight line. Similarly, at k is less than 1, it is some negative value. Okay. And frequency plot is frequency is 0 for this gain k, then this is a 0 representing this log omega and degrees on the y axis. So, the simple the Bode plot for this the transfer function is k. If the transfer function is k, and this is the magnitude plot and this is the phase plot. Now, like similarly, you have to construct the for different factors what we have seen in the tabular form. The if it is a simple the s, that is j omega. Okay. The given transfer function is a simple s j omega, then this magnitude is 20 log omega and the phase angle is 90 degrees. So, at different omega values I have to take and find out the what is the magnitude values. If the omega is equal to 0.1 radians per second and magnitude is obtained minus 20 decibels, if omega is equal to 0, then the magnitude is 0. If omega is equal to 10 radians per second and the magnitude is 20 decibels. So, with this information, just you have to plot the magnitude plot, that magnitude plot is obtained. So, if at 0.1 the value is minus 20 decibels. Okay. So, now we are showing this y axis the magnitude value minus 20 decibels, and at frequency 1, the magnitude is 0, and at frequency 10 this magnitude is plus 20. So, now these are the 3 points and join this line, and the slope of this is plus 20 decibels per decade, plus 20 decibels per decade. So, each decade it increases the 20 decibels. And coming to this phase plot, the phase plot it is 90 degrees. So, it is a plus 90 degrees, above 90 just draw this straight line. So, this is the simple if the transfer function is s, and this is the magnitude plot and phase plot. So, this magnitude plot is a line which is having the slope of 20 decibels. For the description of this graph, once again in this slide is given omega is equal to 0.1 radians per second and the magnitude is minus 20 decibels, and it continues on the same slope, the 20 decibels per decade, and it is touching 0 decibel line at omega is equal to 1 radians per second, and in this case the phase plot is a 90 degrees line. Okay. So, next we will see the second case. Consider this open loop transfer function. If it is g of s into h of s is equal to in the form of 1 plus s t, okay, that is a constant. So, s is equal to j omega. So, now we have to find out the magnitude and phase angle, and substitute at different omega values. Okay, omega is less than 1 by t and the magnitude is 0 decibels and the phase angle is 0 degrees. If omega is greater than 1 by t, then this magnitude is 20 log omega t decibels and the phase angle is 90 degrees. Now, if you look see this how it looks like the magnitude plot and phase plot. Up to this less than 1 by t, this magnitude is 0. So, from 0 it will start from up to here, and this is the point where this the slope will start, and the slope is 20 decibels per decade. Okay. And this phase angle phase angle up to this 1 by t is 0, and from the above this 1 by t the phase angle is 90 degrees. If from here it suddenly increases to 90 degrees and it will move in the same the horizontal line. Okay. So, like this the function is if it is a 1 plus s t, okay, this is the magnitude and the phase plot. So, this is the description about this plot, okay, at different omega values, what are the magnitude and what is the phase angle. Whatever you have seen, how you are constructing the Bode plot, just have shown is a stepwise procedure. The first step what we are going to do is factor the given transfer function into the poles and zeros, how many poles are there and how many zeros are there, factorize the given transfer function, and have to draw find the frequency response from the transfer function of each factor, and use the logarithmic to separate the frequency response into the sum of the decibel terms, and use to find the starting magnitude and the where you can start the magnitude. From the magnitude you have to draw this separate each individual factors, have to draw this magnitude and frequency plots. Then finally you have to combine these two, the magnitude and the phase plots. So, these are the stepwise procedures what just I have explained, that is given in this stepwise procedure. Now, if you see this one or two examples of this Bode plots, how it looks like. This is the logarithmic plot. Okay, we are representing the magnitude on the y axis and the phase angle on the x axis. Okay. So, now this where the slope will start, that is called the break point. Okay. And from this break point it may be the positive slope or it may be the negative slope. If it is a negative slope, the curve will come this downward direction. If it is a positive slope, the curve will goes to the upward direction from that the break point. So, you have to magnitude plot and also have to construct the phase angle plot. Then you have to find out the crossover frequencies, at which frequencies the plots are crossover. Okay, that you have to identify and find out the corresponding to the crossover frequencies, what is the margin values that you are going to find out. Okay, these are the different the examples how we are going to construct the Bode plot. If it is the transfer function is 1 by 1 plus s, and this is the shape of the magnitude plot. If it is a function of 1 by s plus a to the power of r, and this is the shape of the magnitude plot. Okay. Now, in the next session I want to explain in detail about this the typical transfer function I have to consider, and how you are going to calculate all the values, and how you are going to construct the magnitude plot and phase plot will discuss in the next session.